Welcome, folks. Today we are discussing about evolutionary computation for unbalanced classification.
I'm eager to hear about this. What's the core problem this paper addresses?
The main issue is class imbalance in datasets. Many real-world applications like medical diagnosis or fraud detection have datasets where one class, the minority class, has significantly fewer instances than the other, the majority class. This imbalance severely impacts the performance of standard classification algorithms, often leading to biased models that favor the majority class.
So, how does this imbalance affect classifier performance? I mean, what are the practical consequences?
Well, it leads to biased classifiers. They become good at predicting the majority class, but poor at identifying the minority class, which is often the more critical class. For example, in cancer diagnosis, misclassifying a cancer patient as healthy has far more severe consequences than the other way around. Standard metrics like overall accuracy become misleading because they don't reflect the performance on the minority class.
I see. Interesting. So, what are the common approaches to tackle this class imbalance problem?
There are two main categories of techniques: data-level methods and algorithm-level methods. Data-level methods modify the dataset itself to balance the class distribution. This includes techniques like undersampling, reducing the majority class, and oversampling, increasing the minority class. Algorithm-level methods, on the other hand, modify the classification algorithms to handle the imbalance directly. This includes cost-sensitive learning, which assigns different misclassification costs to different classes.
And where does evolutionary computation, EC, fit into all this?
That's the focus of this paper. EC offers a powerful set of tools to address class imbalance. It can be integrated into both data-level and algorithm-level methods. For data-level methods, EC algorithms can be used to intelligently select which instances to keep or remove during undersampling, or to generate synthetic instances during oversampling. For algorithm-level methods, EC can optimize parameters within cost-sensitive learning or even evolve the structure of the classifier itself.
That sounds quite powerful. Can you give me a specific example of how EC is used in a data-level method?
Sure. In undersampling, a common approach is to use a genetic algorithm, GA. Each individual in the GA population represents a subset of the majority class instances. The fitness of an individual is evaluated based on how well a classifier trained on that subset performs on the entire dataset. The GA then evolves the population, selecting individuals with higher fitness, effectively finding the best subset of the majority class to retain while maintaining good classification performance. This is more sophisticated than simply randomly removing instances.
And what about oversampling? How does EC help there?
In oversampling, EC can be used to generate synthetic minority class instances in a more intelligent way than simply duplicating existing ones. For example, techniques like SMOT, synthetic minority oversampling technique, can be improved by using EC to optimize the parameters of SMOT, such as the number of nearest neighbors, to consider when generating synthetic instances. This can lead to more diverse and representative synthetic instances, reducing the risk of overfitting.
That makes sense. But what about algorithm-level methods? How does EC play a role there?
In algorithm-level methods, EC can be used to optimize the parameters of existing classifiers. For instance, in cost-sensitive learning, EC can optimize the cost matrix, assigning different weights to misclassifications of the majority and minority classes. This allows the algorithm to focus more on correctly classifying the minority class. EC can also be used to optimize hyperparameters of classifiers, leading to improved performance on imbalanced datasets.
So, it seems EC provides a flexible framework for handling class imbalance. Are there any limitations or challenges associated with using EC in this context?
Yes, of course. One major challenge is the computational cost. EC algorithms can be computationally expensive, especially when dealing with large datasets. Another challenge is the need for careful parameter tuning. The performance of EC algorithms is highly dependent on the choice of parameters, and finding the optimal parameter settings can be a time-consuming process. Finally, there's the issue of interpreting the results. Understanding why a particular solution evolved by an EC algorithm is optimal can be difficult.
That's a good point. So, to summarize, this paper explores the application of EC techniques to address the problem of class imbalance in classification tasks. It highlights the use of EC in both data level and algorithm level methods, offering a flexible and powerful approach to improve classifier performance on imbalanced datasets, while acknowledging the computational cost and parameter tuning challenges.
Exactly. And the paper provides a comprehensive overview of the existing literature, categorizing different approaches and highlighting promising avenues for future research. Thanks for joining us today, folks. Goodbye.